All right, guys, we are moving into section 7.3, the last part of this section. So we've been talking all about sampling distributions. And now what we're dealing with is we're talking about the sampling distribution of a sample mean. So in order to start, I want to look at this simulation, which we're going to talk about in class as well, where we have a parent population here. And if we notice our parent population here, our parent population is normally distributed. And what we're going to be taking is we're going to be taking samples of size 10 from our population data. So I'm going to take a sample of size 10, and this is my individual sample from my population. And what's being plotted in the blue is a distribution of the sample means. Similar to what we saw with the Reese's Pieces, I'm plotting the distribution of my X bars. So I'm going to do this 5 times, 10 times. I'm going to keep doing this, and I'm going to do it 10,000 times. And once again, similarly, take a look at this. This is the distribution of my sample means. And similar to what we saw with the proportions, okay, I can see that the distribution of my sample means also ends up being approximately normal. But notice that my population was normal. What happens if I take a crazy shaped population? I'm just making my own distribution here. Obviously, this one is clearly skewed right. Okay, so I've created a distribution that's obviously skewed to the right. And I'm going to go through the same process where I'm taking samples of size 10. Actually, I'm going to take samples of size 5 to start. And notice here that the shape is not exactly normally distributed now, my distribution of my sample means. Notice that the parent population was skewed right, and this distribution is still sort of skewed right. But look what happens as we increase our sample size. So we increase our sample size to say 25. Look at how much more normal the distribution of the sample means became. So that's an important concept for you to understand, and we're going to discuss this more in class, but I wanted to give you an idea of what's ahead. So let's go into the notes now. Based on previous simulations, what do we know about the shape, the center, and the spread of the sampling distribution of the sample mean? Well, we know that the shape is going to be approximately normally distributed if something is true, which we're going to talk about. The center, the mean of x bar, mu sub x bar, is an unbiased estimator of mu, and mu sub x bar is equal to mu, meaning the mean of my sample means, if I average all my little individual sample means, that'll be equal to the population mean. And we know as the sample size increases, the standard deviation decreases. Now, specifically, our formulas are on the formula sheet here. So these are all on the formula sheet. Mu sub x bar, the mean of the sampling distribution, is equal to the population mean. Sigma sub x bar. So we saw our formula for proportions. Now we have a new formula for means. Sigma sub x bar, the mean of the sampling distribution, is equal to your population standard deviation over the square root of n. So what you have to know is anytime your sample size is changing, your standard deviation is going to change. And as the sample size increases, the standard deviation is going to decrease, as we saw before. There is a condition for using this formula, and that formula is our independence condition, that our sample size must be less than or equal to 1/10 of the population size. It's our 10% condition. What about normality, which is what we saw in that simulation? Well, we saw it depends. It depended on two things, the population size and the sample size. So if we take a look at this graph right here, we see that this population distribution is clearly skewed to the right. We're taking samples of size 100, and we're looking at the mean household earnings in the samples of size 100 and plotting these are my X bars. Notice that even though the population distribution was skewed right, the sampling distribution is approximately normal. So there's two parts to this that are important. Part 1 says if the parent function is normally distributed, meaning if my original function is normally distributed here, my parent function, regardless of the sample size. Doesn't matter the sample size. The sampling distribution is always approximately normal. Doesn't matter if I'm taking samples of size 100, taking samples of size 5, taking samples of size 10. If the parent function or the population is normally distributed, then the sampling distribution automatically normally distributed regardless of the sample size. That is an important concept. So that's like your get out of jail free. Population normal, sampling distribution automatically normal. If the population distribution is not normal, so if we have this population that's some crazy shape, maybe it's bimodal, maybe it's skewed, maybe it's whatever, then we refer to this other concept here, which is the central limit theorem. The central limit theorem is one of the most important theorems in all of statistics. And it answers a question about what is the shape of the sampling distribution when it's not a normally distributed population. So when our population is not normal, when it's something crazy like a bimodal shape or skewed, that's where the central limit theorem comes into play. And the central limit theorem says if the population distribution is not normal, the sampling distribution of X bar will be considered approximately normal once we reach a sample size of 30, okay? Until we reach that sample size of 30, the sampling distribution is not considered approximately normal. That sample size needs to be at least 30. So the central limit theorem, formal definition, for large samples, n greater than or equal to 30, and that's your breaking point, the sampling distribution of X bar will be approximately normal. Once you reach that sample size of 30, that's your threshold. Sampling distribution up, approximately normal, regardless of population size. This central limit theorem is only used when we are talking about a mean problem, okay? When we're talking about the mean problems, we use this sampling distribution in this central limit theorem. This does not apply to proportion problems, only for means. For small samples, when n is less than 30, the shape of the sampling distribution resembles the population distribution. So central limit theorem says when the sample size is greater than or equal to 30, the sample size is automatically approximately normal. Doesn't matter the population size. So just to kind of reiterate, what is the sampling distribution? It's a graph of every single possible value of all of my X bars. It's a graph of all your little individual X bars in this case, because we're talking about means. So mu sub X bar is equal to mu. Sigma sub X bar is equal to the population standard deviation over the square root of n. We'll be looking at multiple examples in class illustrating all of this information. See you then.